Welcome to Nano ENC Lab Journal Club meeting. I am Dr. Siva from Nano ENC Lab, Ajou University, South Korea. Today I am going to discuss a research article entitled High-Entropy Alloys as Catalyst for the CO2 and CO reduction reactions. Experimental realization. This research article was published in ACS Catalysis by Nelayapan et al. These are the content I am going to discuss in the following discussion. First, I am going to explain the importance of CO2 conversion, including electrocatalytic CO2 aura and their advantages. And then I am going to introduce the high entropy alloy. As an electrocatalyst, what are the advantages we can get from this high entropy alloy? Finally, I am going to explain this research article. In this research article, first I am going to talk about the synthesis of gold, silver, platinum, palladium, copper, high entropy alloy nanoparticles and the material characterizations, and end up with electrochemical CO2 performance with summary. From this global CO2 graph, it's clearly observed that every year the global CO2 emission is gradually increasing, and also it strongly influences in the global warming, even it leads the global warming. Over time, high temperature can change the weather pattern, so the frequent climate change may occur. And also the global warming is strongly influencing in the wildfires and ice rocks melting. These all the things may be a risk to human beings and other living. So it is very urgent and very important to control the global CO2 emission, or else the CO2 should be converted into other value added products. So that there are many methods have been employed so far to convert the CO2 efficiently into other products, including photocatalytic method by using a solar light, and electrocatalyst by using electricity, and photo electrocatalyst method. It's a combination of photo and electrocatalytic method. Among these various techniques, electrochemical and photoelectrochemical approaches are considered as a potential method to obtain the high Faradaic efficiency with high selectivity. And also these techniques having the options for wide catalyst choice, so that the selectivity and efficiency can be effectively controlled and it can be viable for large scale. During the electrocatalytic CO2 the electrical energy alone act as a driving force to reduce the CO2 into other value added products such as fuels and chemicals at the surface of the electrocatalyst. And this is the typical electrochemical CO2 reduction cell designs. Here currently two different kind of cells are used in CO2 electrocatalytic CO2 that are flow cell and MEA cell. So here the advantage of this electrocatalytic CO2 is, here we were able to achieve high energy efficiency and high current density with high stability as compared with all other techniques. And also in this electrocatalytic CO2 RR, the critical and the most important part is the catalyst design, because on the catalyst surface the CO2 is effectively converted into various value added products including fuels and other chemicals. So to find or design the electrocatalyst is a critical in this electrocatalytic CO2 RR. Accordingly, various types of electrocatalysts such as noble metals and non-noble metals are employed in the electrocatalytic CO2 RR. In the case of precious or noble metals, platinum, gold and Ag nanostructures are widely used, and the researchers achieved high electrocatalytic performance with high selectivity. But there are two problems with these noble metals. One is the noble metals, particularly the platinum, can easily poisoned by the carbon monoxide. This carbon monoxide formation is most feasible while converting the CO2 into other value added products. So this platinum poisoning by CO2 is an unavoidable reaction with these noble metals. And other big problem is the scarcity of these noble metals on the earth's surface. So it means the cost of these noble metals are very high. So due to these two reasons, it is little difficult to expand the research on these noble metals towards the large scale applications. So recently the researchers are trying to find non-noble metal based electrocatalyst which can able to achieve moderate or high electrocatalytic performance or selectivity as that of noble metals. In that case, currently copper metal is considered as one of the potential candidate to achieve a better performance as compared with all other noble metal catalysts like tin and manganese, zinc and all. But here when we compare with the noble metals, the problem is it cannot achieve the electrocatalytic performance as that of noble metals, and here the selectivity also very limited with moderate stability. So the noble metal itself, it is not efficient to improve the electrocatalytic performance and particularly the selectivity. So recently the researchers are trying to find or trying to make suitable metal alloys with multiple metals so that the metal alloys can easily control the selectivity of the products with improved electrocatalytic performance. So the researchers are focusing on the synthesis of various metal alloys and try to introduce in the electrocatalytic CO2 RR reactions. Recently, high entropy alloy, so it called as HEA, is a new class of material. It consists of minimum 5 major elements with high configurational entropy. And also due to the multiple atoms existence in a HEA, their crystal lattice shows strong distortion. So due to these parameters, the high entropy alloy shows the unique and advanced properties as compared with other conventional alloys. For example, it shows a unique and ideal surface structures with multiple active sites. Against the environment, it has very strong corrosion resistance. And another most important thing is that it is easy to control the elements. It means the tunability is high. So based on this, currently the high entropy alloy is considered as one of the potential electrocatalyst for various electrochemical applications. As a catalyst in the electrochemical applications, the high entropy alloy shows multiple advantages. For example, the catalyst surface consists of multiple atoms, so it shows unique charge distribution, and the different structures gives the coordination effect, and the different elements gives the ligand effects, and these two effects are leads the disorder element arrangements with high synergetic effect. And also the multiple elements shows the distinct work functions towards the catalytic process with low energy barrier. So overall, this high entropy alloy have multiple advantages as compared to the conventional alloy in the electrochemical applications. So it is considered as a potential candidate for the electrocatalytic CO2 Accordingly, in this research article, the precious metal based high entropy alloy nanoparticles such as gold, silver, platinum, palladium, copper based high entropy alloy nanoparticles was synthesized by combining melting and cryomilling process. It's called cast cum cryomilling process. For that, first the high pure gold, silver, palladium, platinum and copper nano powders were melted under argon atmosphere and form the cast gold, silver, platinum, palladium, copper HEA. After that, by using the customized single ball cryomill setup, this is the typical setup which they have used to break this into the nanoparticles. Here they used like airtight container with tungsten carbide walls with the tungsten carbide vial, and also they use the liquid nitrogen to keep the temperature below 0 degrees Celsius. Here they use an inert atmosphere of argon to keep this portion inert without any atmospheric air influence to avoid the pre-oxidation of the metal in the high entropy alloy. So after forming this one, so they take this cast gold, silver, platinum, palladium, copper high entropy alloy and put it here, and then they did the milling for 6 hours, and here they filled with the liquid nitrogen, so they can able to keep the temperature minus 160 degrees Celsius. After 6 hours, they were collected the gold, silver, platinum, palladium, copper high entropy alloy nanoparticles for further characterizations and to test the electrochemical CO2. First, they perform the X-ray diffraction and transmission electron microscope analysis to confirm the formation of crystal structure and confirm the nanoparticles formation. So from the typical XRD pattern, it is confirmed that the high entropy alloy has a single phase with phase centered cubic crystal structures, and the calculated lattice parameter of this FCC high entropy alloy is 0.3936 nanometer. So the single phase high entropy alloy do not have any impurities. And then this is the typical TM image. So from this TM image, it's very clear that after the grinding, the cast gold, silver, platinum, palladium, copper was uniformly break and form the nanoparticles with the average size of 16 nanometer. And then the authors were used HR stem and APT analysis to confirm the lattice arrangements of various atoms and their distribution in the atomic level. So from this HR stem image, it is very clear that all different atoms with different intensity are arranged in the 001 lattice of gold, silver, palladium, platinum, copper high entropy alloy. And also this uniform elemental distribution of all 5 elements in the atomic level confirms the perfect formation of high entropy alloy in the FCC matrix without any aggregations. Finally, the authors were performed the X-ray photoelectron spectroscopy, that means XPS analysis, to understand the surface oxidation, it means surface chemical oxidation of each elements in the high entropy alloy. So from these high resolution XPS spectrum and their peaks, it's confirmed that all the elements are showing their metallic oxidation state without any surface oxidation. It confirms the stability of the high entropy alloy in the environment. Unfortunately, there is a small amount of copper 2 plus which might be due to the effective charge transfer between the nearby atom of silver and copper. The cyclic voltammetry behavior of the high entropy alloy was tested in 0.5 molar K2SO4 solution with a scan rate of 40 millivolt per second. The predominant redox peak appeared at A1 and C1 is corresponding to the redox reaction of copper 2 plus and CuO. And another oxidation reduction peak which is appeared at A2 and C2 is a typical behavior of platinum and Au in the high entropy alloy. Interestingly, when the cyclic voltammetry window is narrowed from 0 to -1, the predominant peak which is appeared at A1 becomes broad and exists with a shoulder peak, and in the reduction side the peak is not clearly visible. So it confirms that the partial surface oxidation of copper 2 plus and copper 0 in the high entropy alloy. And This predominant copper 2 plus and copper 0 peak in high entropy alloy confirms that copper atom is the most active catalyst in this high entropy alloy. And also the release sweep voltammogram was performed in same electrolyte with a scain rate of 20 millivolt per second. Here this nitrogen blank is nothing but nitrogen saturated electrolyte. So when they use this nitrogen saturated electrolyte, the current density at minus 0.8 volt is very low. It's about 2.2 milliampere per centimeter square. But interestingly, when they have used CO2 saturated 0.5 molar K2SO4 electrolyte, that time they can able to see a clear peak with a highest current density of 10.15 milliampere per centimeter square, which is almost 5 times higher than that of the nitrogen saturated electrolyte condition. So it confirms that the HEA is highly active for the CO2 reduction. And also the current efficiency were calculated by using this formula. So here ICO2 is the current density obtained from CO2 saturated electrolyte, and I blank is the current density which was obtained from the nitrogen saturated electrolyte. From this inset graph, it is very clear that at minus 0.8 volt, the current efficiency is about 81.8%, which is obtained from this CO2 saturated electrolyte, which is due to the CO2 reduction reaction. Also, the electrochemical CO2 RR of this high entropy alloy was tested in 0.5 molar sodium bicarbonate electrolyte because it is one of the commonly used electrolyte in CO2 RR. So this is the typical linear sweep voltammogram which was measured in 0.5 molar sodium bicarbonate solution with N2 saturation and CO2 saturation. If you compare this blank and CO2 LSV, there is no current density difference. So it means the gold, silver, palladium, platinum, copper high entropy alloy is not active in this electrolyte for the CO2 RR. From this observation, it is clear that the HAs are strongly independent with the pH of the electrolyte. The steady state current responses of the high entropy alloy were tested in CO2 saturated 0.5 molar K2SO4 electrolyte. This is the typical chronoamperometry spectrum, which was measured at different applied potential of minus 0.7, minus 0.8 and minus 0.9 volt. This inset bar diagram is clearly shows the obtained current density as different potentials. The maximum current density of 13.8 milliampere was achieved at minus 0.5 volt. So it means the high entropy alloy shows an impressive CO2 electrocatalytic activity at a potential of minus 0.9 volt. And this is the typical Faraday efficiency graph. So here the Faraday efficiency were calculated for 4 different products. So actually these 4 different products are almost similar to the copper based electrocatalyst. So it explains that the copper is doing the predominant role and other metals are doing some synergetic effect to improve the electrocatalytic activity of the high entropy alloy. Here the Faraday efficiency was calculated by using this formula where N is the number of electron transfer, F is the Faraday constant, and N is the amount of the generated product in this process, and Q is the total charge passed through the whole reaction. Interestingly, the CO2 interestingly the CO Faraday efficiency is very low at all 3 potentials of minus 0.7, minus 0.8 and minus 0.9. Comparatively, the CH4 and C2H4 formation is predominant, with a Faraday efficiency of 49.4 and 19.9 percentage even at a low potential of minus 0.7 volt. Importantly, the total Faraday efficiency is 100% even at a low potential of minus 0.7 volt for the gaseous products. So it means there is a zero or negligible liquid products formation during the CO2 RR reaction activity. So it highlighting the unique capability of the high entropy alloy to produce 100% gas products without any liquid products. And the CO2 RR activity was compared with other nano catalysts that are non-HE actually. So here if we compare with different catalysts like copper, Ag, Au and palladium, among all this HEA can achieve 100% Faraday efficiency even at a lower potential of minus 0.3 volt versus RHE. So it means this high entropy alloy comparatively requires very low applied potential. Even at low applied potential, it can efficiently sticking the hydrocarbons towards the efficient CO2 reaction activity. Also, the long-term stability of the high entropy alloy was measured by using chronoamperometry technique. So here the CO2 is continuously bubbled with 0.5 molar K2SO for electrolyte. So the stability test was carried out at minus 0.8 volt for 5 hours. Initially, the high entropy alloy shows a small current density loss, which might be due to the instability of the electrode surface at the initial stage. After a few seconds, the stability was almost stable for 5 hours. So it shows that high entropy alloy having good stability in 0.5 molar K2SO. Finally, Gibbs free energy was calculated by using density functional theory and compared with the copper FCC111 facet. The intermediate's conversion from OCH3 to O is the rate determining step with high potential barrier of 1.91 electron volt. At minus 0.35 volt, copper 111 surface requires more extra potential to overcome this uphill conversion step from OCH3 to O. So but in the case of high entropy alloy, this step requires very less potential to overcome this reaction. So it confirms that the destabilization of OCH3 and the stabilization of O intermediate is happened on the surface of the high entropy alloy, which might be due to the existence of multiple elements in the high entropy alloy electrocatalyst compared to the metallic copper. This is the summary of this research work. The gold, silver, platinum, palladium, copper high entropy alloy nanoparticles were successfully demonstrated as a efficient catalyst for the electrochemical CO2 RR. Different characterizations confirms the successful synthesis of a single phase-centered cubic high entropy alloy with uniform metal distributions. The predominant copper redox property from the cyclic voltammetry confirms that the copper metal is doing the predominant role in the CO2 RR activity, and other metals doing the good synergetic effect to enhance the CO2 RR performance. Interestingly, even at low potential of minus 0.3 volt was RHE, this high entropy alloy can achieve 100% conversion efficiency of CO2 but to gaseous products, which highlights the uniqueness of the high entropy alloy. From the DFT calculation, high entropy alloy is a unique and efficient catalyst for the enhanced electrocatalytic CO2 reduction compared with the Preston. Thank you for your kind attention.